let's see. I now have to rebuild the model of computation so you understand how some such mechanical mechanism could work that can do what we've just talked about. I've just recently destroyed your substitution model. Unfortunately, this model is significantly more complicated than the substitution model. It's called the environment model. And I'm going to have to introduce some terminology, which is very good terminology for you to know anyway. It's about names, and we're going to give names to the kinds of names things have and the ways names are used. Okay, so this is a meta description, if you will. Anyway, there's a pile of unfortunate terminology here, but we're going to need this to understand what's called the environment model. And we're about to do a little bit of boring dog work here. Let's look at the first transparency. And we see a description of a word called bound. Okay. And we're going to say that a variable v is bound in an expression e if the meaning of e is unchanged by the uniform replacement of a variable w not occurring in e for every occurrence of v in e. Now, that's a long sentence. Okay, so I think I'm going to have to say a little bit about that before we even fool around at all here. Bound variables we're talking about here. And you've seen lots of them. You may not know it, you've seen lots of them, although I suppose in your logic you saw logical variables like for every x there exists a y such that p is true of x and y from your calculus class. Okay. This variable x and this variable y are bound because the meaning of this expression does not depend upon the particular letters I use to describe x and y. If I were to change w for x, so this said for every w there exists a y such that p is true of w and y, it would be the same sentence. That's what it means. Or another case of this that you've seen is integral, say from 0 to 1 of dx over 1 plus x squared. Okay. Well, that's something you see all the time, and this x is a bound variable. If I change that to a t, the expression is still the same thing. This is a quarter of the arctan of 1 or something like that. It's arctan of 1. So bound variables are actually fairly common for those of you who've played a bit with mathematics. Well, let's go into the programming world. Instead of the quantifier being something like for every, or there exists, or integral, a quantifier is a symbol that binds a variable. And we're going to use the quantifier lambda as being the essential thing that binds variables. And so we have some nice examples here, like that procedure of one argument y, which does the following thing. It calls the procedure of one argument x, which multiplies x by y, and applies that to 3. That procedure has the property that there are two bound variables in it, x and y. This quantifier lambda here binds this y, and this quantifier lambda binds that x. Because if I were to take an arbitrary symbol that does not occur in this expression, like w, and replace all y's with w's in this expression, the expression is still the same procedure. And this is an important idea. The reason why we have such things like that is a kind of modularity. If two people are writing programs, it should be, and they work together, it shouldn't matter what names they use internal to their own little machines that they're building. Okay? And so what I'm really telling you there is that, for example, this is equivalent to that procedure of one argument y, which uses that procedure of one argument z, which multiplies z by y, because nobody cares what I used in here. Okay? It's a nice example. On the other hand, I have some variables that are not bound. An example. That procedure of one argument x which multiplies x by y. In this case, y is not bound. Supposing y had the value 3, okay, and z had the value 4, okay, then this procedure would be the thing that multiplies its argument by 3. If I were to replace every instance of y with z, I would have a different procedure which multiplies every argument is given by 4. Okay, and in fact, we have a name for such a variable. Here, we say that a variable v is free in an expression e if the meaning of the expression e is changed by the uniform replacement of a variable w not occurring in e for every occurrence of v in e. Okay, so that's why this variable over here, y, is a free variable. And so, free variable in this expression. And other examples of that is that procedure of one argument y, which is just what we had before, which uses that procedure of one argument x that multiplies x by y. Use that on 3. This procedure has a free variable in it, which is asterisk. See, because if that has the normal meaning of multiplication, then if I were to replace uniformly all asterisks with pluses, then the meaning of this expression would change. That's what you mean by a free variable. So far you've learned some logician words which describe the way names are used. Now we have to do a little bit more playing around here. A little bit more. I want to tell you about the regions over which variables are defined. You see, we've been very informal about this up till now. And of course, many of you have probably understood very clearly, or most of you, that the x that's being declared here is defined only in here. Okay? This x is defined only in here, and this y is defined only in here. Well, we have a name for such an idea. It's called a scope. And let me give you another piece of terminology. It's a long story. If x is a bound variable in E, then there is a lambda expression where it is bound. So the only way you could get a bound variable ultimately is by a lambda expression. Then you may worry, there's defined quite this, an exception to this. And it turns out we can always arrange things so you don't need any defines. And we'll see that in a while. It's a very magical thing. Okay, so define really can go away. Okay, the really only thing that makes names is lambda. That's its job. And what's so amazing about a lot of things is that you can compute with only lambda. But in any case, okay, a lambda expression has a place where it declares a variable. We call that the formal parameter list. And we say, or the bound variable list. We say that the lambda expression binds, so it's a verb, binds the variables declared in its bound variable list. And in addition, those parts of the expression where the variable is defined, which was declared by some declaration, is called the scope of that variable. So these are scopes. This is the scope of y. And this is the scope of x. That sort of thing. Okay. Well, now we have enough terminology to begin to understand how to make a new model for computation. Because the key thing going on here is that we've destroyed the substitution model, and we now have to have a model that represents the names as referring to places. Because if we're going to change something, then we have to have a place where it's stored. You see, if a name only refers to a value, and if I tried to change the name's meaning, well, that's not clear. There's nothing that is the place that name referred to. Or how am I really saying it? There's nothing shared among all of the instances of that name. And what we really mean by a name is we've fanned something out. We've given something a name, and you have it, because I've given you a reference to it, and I've given you a reference to it. And we'll see a lot about that. So let me tell you about environments. I need the overhead projection machine. Thank you. Okay, so here is a bunch of environment structures. An environment is a way of doing substitutions virtually. It represents a place where something is stored, which is the substitutions that you haven't done. It's a place where everything accumulates, where the names of the variables are associated with the values they have, such that when you want to say what does this name mean, you look it up in an environment. So an environment is a function, or a table, or something like that. But it's a structured sort of table. It's made out of things called frames. Frames are pieces of environment, and they're chained together in some nice ways by what's called parent links or something like that. So here we have an environment structure consisting of three environments, basically: A, B, and C. D is also an environment, but it's the same one. They share. And that's the essence of assignment. If I change a value of a variable that lives here, like that one, it should be visible from all places that you're looking at it from. Say this one, x. If I change that x to 4, it's visible from other places. But I'm not going to worry about that right now. We're going to talk a lot about that in a little while. What do we have here? Well, these are called frames. Here's a frame, and here's a frame. A is an environment which consists of the table labeled, which is frame 2, followed by the table labeled frame 1. And in this environment, in say this environment, frame 2, x and y are bound. They have values. In frame 1. In frame 2, z is bound, and x is bound, and y is bound. But the value of x that we see looking from this point of view is this x. Its x is 7, rather than this one, which is 3. We say that this x shadows this x. Okay? From environment 3, from frame 3, from environment B, which refers to frame 3, we have variables m and y bound, and also x. Okay. This y shadows this one. So the value, looking from this point of view, of y is 2. The value, for looking from this point of view, of m is 1. And the value, looking from this point of view, of x is 3. So there we have a very simple environment structure made out of frames. These correspond to the applications of procedures. And we'll see that in a second. So now I have to make you some other nice little structure that we build. On the next slide, we see an object which I'm going to draw procedures. This is a procedure. A procedure is made out of two parts. It's sort of like a cons. Okay. However, it's the two parts. Okay. The first part refers to some code, something that can be executed, a set of instructions, if you will. You can think of it that way. And the second part is an environment. The procedure is the whole thing. And we're going to have to use this to capture the values of the free variables that occur in the procedure. If a variable occurs in the procedure, it's either bound in that procedure or free. If it's bound, then the value will somehow be easy to find. Okay? But I will talk, it'll be in some easy environment to get at. If it's free, we're going to have something that goes with the procedure that says where it'll go look for its value. And the reasons why are not obvious yet, but will be soon. So here is a procedure object. It's a composite object consisting of a piece of code and a environment structure. Now I will tell you the new rules, the complete new rules for evaluation. Okay. The first rule, there's only two of them. These correspond to the substitution model rules. And the first one has to do with how do you apply a procedure to its arguments. Okay. And a procedure object is applied to a set of arguments by constructing a new frame. That frame will contain the mapping of the formal parameters to the actual parameters of the arguments that were supplied in the call. As you know, when we make up a call to a procedure like lambda x times xy, and we call that with the argument 3, then we're going to need some mapping of x to 3. It's the same thing as later substituting, if you will, the 3 for the x in the old model. So I'm going to build a frame which contains x equals 3 as the information in that frame. Now, the body of the procedure will then have to be evaluated, which is this. And it will be evaluated in an environment which is in the environment which is constructed by adjoining the new frame that we just made to the environment which was part of the procedure that we applied. So I'm going to make a little example of that here. Supposing I have some environment, here's a frame which represents it, and some procedure, which I'm going to draw with circles here because it's easier than little triangles. Sorry. Those are rhombuses. Rhomboidal little pieces of fruit jelly or something. So here's a procedure which takes this environment. And the procedure has a piece of code which is a lambda expression which binds x and y and then executes an expression e. And this is the procedure. We'll call it P. I wish to apply that procedure to 3 and 4. So I want to do P of 3 and 4. Well, what I'm going to do, of course, is make a new frame. I build a frame which contains x equals 3 and y equals 4. And I'm going to connect that frame to this frame over here. Okay. And then this environment, which I will call B, is the environment in which I will evaluate the body of E. Now, E may contain references to x and y and other things. X and y will have values right here. Other things will have their values here. How do we get this frame? That we do by the construction of procedures, which is the other rule. And I think that's the next slide. Rule 2. When a lambda expression is evaluated relative to a particular environment, see, the way I get a procedure is by evaluating a lambda expression. Here's a lambda expression. By evaluating it, I get a procedure which I can apply to 3. Now, this lambda expression is evaluated in an environment where y is defined. And I want the body of this, which contains a free version of y. Y is free in here. It's bound over the whole thing, but it's free over here. I want that y to be this one. I evaluate this body of this procedure in the environment where y was created. That's this kind of thing, because that was done by an application. Now, if I ever want to look up the value of y, I have to know where it is. Therefore, this procedure that was created, the creation of the procedure, which is the result of evaluating that lambda expression, had better capture a pointer or remember the frame in which y was bound. Okay, so that's what this rule is telling us. So, for example, if I happen to be evaluating a lambda expression in E, lambda of, say, x and y, let's call it g in E, evaluating that, well, all that means is I now construct a procedure object. E is some environment. E is something which has a pointer to it. I construct a procedure object that points off to that environment, where the code of that is the lambda expression or whatever that translates into. And this is the procedure. So this produces for me, this object here, this environment pointer, captures the place where this lambda expression was evaluated, where the definition was used, to make a procedure, to make the procedure. So it picks up the environment from the place where that procedure was defined, stores it in the procedure itself, and then when the procedure is used, the environment where it was defined is extended with the new frame. So this gives us a locus for putting where a variable has a value. And for example, if there are lots of guys pointing at that environment, then they share that place. And we'll see more of that shortly. Well, now you have a new model for understanding the execution of programs. I suppose I'll take questions now, and then we'll go on and use that for something.
Is it right to say then the environment is that linked chain of frames?
That's right.
Starting with working all the way back?
Yes. The environment is a sequence of frames linked together, and the way I like to think about it is the pointer to the first one. Because it's, once you've got that, you've got them all. Anybody else?
Is it possible to evaluate a procedure or to define a procedure in two different environments such that it will behave differently and have pointers to both?
Oh, yes. The same procedure is not going to have two different environments. The same code, the same lambda expression, can be evaluated in two environments producing two different procedures. Each procedure...
Their definition has the same name, their operation...
The definition is written with the same characters. I can evaluate that set of characters, whatever, or that list structure that defines, that is the textual representation. Okay? I can evaluate that in two different environments producing two different procedures. Each of those procedures has its own local sets of variables, and we'll see that right now. Okay? Anybody else? Okay, thank you. Let's take a break.